So we are going to see some standard sorting algorithms in this lecture. As we know, sorting is one of the fundamental problem in computer science, and it has tons of applications. So we don't really need too much of a motivation. Right, so let's start with one of the simplest sorting algorithm known as selection sort. Selection sort. And it works this way. You are given an array of n numbers. Okay, you are given an array of n numbers. In this case, n is 6, and we need to sort them. So the selection algorithm works in n steps. So basically do this in n steps. In step 1, you will go through the entire array and find the smallest element. Okay, so go through the entire array, find the smallest element, which is nothing but 3. Now, I know that at the end of the algorithm, 3 has to be at the first position. So what I will do is, I'll just move this 3 here and put this 5, that is the first element, to the position corresponding to 3. Essentially, I make a swap between these two numbers. So now the new array will look like 3, 4, 9, 7, 5, 8. So now I can forget about this part of the array because I'm done with it. Now I just need to worry about the remaining part of the array. I just need to sort the remaining part of the array, right? To sort the remaining part of the array, simply do the same procedure. That is, find the smallest element, which is 4 in this case, and move to the first position in this part of the array. In this case, 4 is the smallest, so we don't have to do anything. So after 2 steps, the array will look like 3, 4, 9, 7, 5, 8. And we are done with this part. Done with this part. And we just need to sort the remaining part. Again, we do the same thing. Find the smallest, which is 5, and move it here, and move this thing here. So the new array will look like 3, 4, 5, 7, 9, 8, so on and so forth. Right? And this is the algorithm. It's pretty easy to see that this is correct, because what we are doing at the kth step is bringing the kth smallest element to position k, and all the elements before that position are already in the right position. Okay, so that way we can easily prove that this algorithm is correct. Now, to bound the time complexity, what you can see here is the first step is going to take roughly n comparisons, because we have to scan the entire array, and we might end up in doing one swap. So roughly n time for the first step. The second step need the same procedure, but on an array of smaller size, right? And on an array of size n minus 1. So the second step will need n minus 1, third is n minus 2, dot dot dot. The last step will need 1. So if you sum this up, this is big O of n squared. So that is the complexity of selection sort. The next sorting algorithm is insertion sort. And insertion sort works this way. I'm using the same example. So insertion sort, in the first step, is going to have a look at the first two elements and check if they are in the sorted order. If they are, do nothing. If they are not, just make sure that these two elements are in the sorted order. In this example, you see 5 and 4 are not in the sorted order. So just rearrange them and sort it. So 4 will come here, 5 will come here. The rest of the array will stays the same. This is the first step. So now I know that these two elements are in the sorted order. In the next step, what I will do is I'll check the next element and I will see if the first three elements are in the sorted order. To ensure that, all I need to do is check or basically compare this element with the previous element. If the previous element is smaller than this, I can ensure that the first three elements are in the sorted order, which is true in this case. The first three elements are already sorted, so do nothing. So that is the third step. So third step essentially is just one comparison and the array will stay the same. So at the end of third step, the array will look the same, and I know that this array is now, the first three elements are sorted. Next step, we're going to have a look at the next element and check if the first four elements are sorted. And for that, what I'm going to do is I will try to compare this element, because this is a new element, right? So I will see if, I'll just compare this with the previous number, which is 9, and I see that 9 and 7 are not in the right order. 9 has to go after 7. So why don't we just swap them? So we'll just make a swap and I'll keep 9 here and I will try to keep 7 at the place of 9. And I will try to compare whether 7 is now at the right place. So for that, all I am doing is I will compare 7 with the previous number and I see that 5 is a smaller numbers and all the numbers before that are also going to be smaller. That means now the first four elements are sorted. So at the end of this step, the array will look like this. Now what I will do is pick the next number. So the array will look like this. Now pick the next number and I want to check if all the elements from the beginning until this number are in the sorted order. So all I'm going to do is compare 3 with 9 and I see they are not in the right order, so I have to replace or basically swap them, right? So 9 has to come here and 3 has to go in this place. But now I see, once I keep 3 here, I need to ensure that 3 is more than the previous number, which is not true. So that means 7 and 3 has to be swapped. So 7 will come here, 3 will come here. Is 3 in the right place now? No, because 5 is more than 3. So I have to swap these two things again. So 5 will come here and 3 will come here. Check again. I need one more swap. So 3 will be here, 4 will be here. Now I check the last number, which is, 8 is going to be here. Check the last number and I see that I need a swap. So I'll swap 9 and I'll keep 8 here. Now I see that 8 is larger than 7. So that means the rest of the array is fine. And now that I have reached the end of the array, I have the output. Why is this algorithm correct? Because what I'm actually doing is at the end of k steps, I'm sorting the first k elements in this array. That is my claim. Okay, I'm claiming that at the end of k steps, my algorithm will sort the first k elements. And how to prove this? I can use mathematical induction, right? For k is equal to, let's say, 1 or 2, the base case is true, and assume it is true for some some general k and prove it for k plus 1. All of these are pretty straightforward. That means at the end of the day, k is going to be n. That means you have the whole array sorted. So that is a proof of correctness. Now I just need to bound the time complexity. What you can see here is the first step, right? The first step we are comparing just two elements. So I need one comparison and I might need one swap. The next step, I will do one comparison, then I might have to do a swap. Then I will do one more comparison, and that might ask you to do one more swap. So in general, the kth step might end up having around k minus 1 comparisons and k minus 1 swaps, right? In the worst case, the kth step is going to cost you roughly k time. That means overall, time complexity in the worst case is going to be k is equal to 1 to n, which we know as big O of n square. Next we have merge sort. Okay, so merge sort works this way. It is actually a divide and conquer strategy. So this is one of the basic technique we use in algorithms to solve many problems. So the idea is this: your task is to sort an array A. So let's say this is array A and the size of A is n, okay, and we want to sort this array. What we will do is, first we will divide this array into two sub-arrays, a left part and a right part. If possible, both are of the same size, like n over 2 and n over 2. And we call this part as A1 and this part as A2. Right? If n is an odd number, then you will have one extra element in one of these sides. So the problem of sorting A, that is sort A, we are going to somehow convert into the following task. You will divide, then you will sort the left part, you will sort the right part, okay? Now we have two sorted arrays and somehow we merge these two sorted arrays and we will get sorted A. So essentially the first part is you sort A1, then you sort A2. What you do is you take these outputs and simply merge them. So essentially this is the algorithm. The thing is merging two sorted arrays is a much easier task than sorting. For example, suppose we have an array, we have two arrays here, both are sorted. So let me just put some numbers, 3, 5, 8, etc. 2, 4, 9, etc. And you want to merge them, both are sorted and you want to merge them. You want to merge and make a new array which is again sorted. So what you need to do is you want to find the minimum, right? So for that, what you can do is have a look at the current minimums in both these arrays and pick the smallest. So the current minimum here is 3 and 2, and among these two the smallest is 2, so just simply pick 2 and write it here. Now have a look at the new current minimums, which are 4 and 3, and pick the minimum among them, which is going to be 3. So here it is 3, and now the current minimum for the first array will change. So again pick the current minimum, and so on and so forth. So this merging can be easily done in time proportional to the size of these arrays, that is in linear time. Okay, so therefore the time for sorting array A is equal to the time for sorting A1 plus the time for sorting A2 plus the time for merging the output. So if I use T of n, to represent the time complexity of sorting A, then this will take Tn over 2, so total 2 times Tn over 2, and the merging step as I sort can be done in linear time, that is some constant times n, and if you solve this recursion, what you will get is, you can make it as 4 times 2 times 2t n over 4 plus cn over 2 plus cn, which will be 4 times tn over 4 plus 2 times cn, and if you expand it further, let's say up to k times, then you will get something like this: 2 to the k tn divided by 2 to the k plus k times c times n. Now what you can see here is, on the right hand side, this is the only term which is unknown, but what we know is, when this quantity is a constant, when what is inside the bracket is a constant, we can say that t of a constant is a constant, because pretty much all problems can be solved in constant time if the input size is a constant. So we can assume that, so to make this quantity a constant, let's say 1, you should have n is equal to 2 to the k, or k is equal to log n, and if you plug in these things back here, this will become n into t of 1 plus log n times c times n, and the whole thing will become big O of n log n. So the time for merge sort is big O of n log n. Okay, so one thing I want you to notice at this point is the basic operation we have used in all of these sorting algorithms is comparison, which means comparison is the only way to figure out if one element is equal to the other one, or greater or less. Okay, so that is why these algorithms are called comparison based sorting algorithms. Comparison based sorting algorithms. Okay, so in summary, we have selection sort and insertion sort, which takes quadratic time, and now we have an improved algorithm called merge sort, which can do the job in n log n time. So the question remaining is, can we improve this time complexity further? In other words, can we come up with a new algorithm which has a time complexity better than big O of n log n? Better than big O of n log n means small o of n log n. Okay, and the answer to this question is what we're gonna see next, which is essentially a lower bound for comparison based sorting algorithms, and we will prove that merge sort is essentially optimal. That means any sorting algorithm, any comparison based sorting algorithm must take this time. We're going to show that.